Okay, so we discuss about the structural design of flexible pavement. We are starting with that from this week. So if you look at your module 7, these are the things that you have discussed in the lecture. So multi-layered structure of flexible and rigid pavements, outline differences between flexible and rigid pavements. You already know that. But now, when we are moving to structural design part, we need to know how the load is distributed in flexible pavement and rigid pavement separately. Discuss factors influencing material performance, project reliability, construction and maintenance, environment. So we are going to discuss today as well in one of the questions. Introduce mechanics 6 models for flexible pavement design. Introduce damage models for asphalt, cemented materials, and subgrade. We will discuss these things next week for when we are going to do a example of structural design part, because we need to know in different layers where are the critical points the failure can happen, and we are going to use that for the design, finding the right materials and finding the right thicknesses of different layers. Austroads sublayering. So we are going to do a question. So these ones actually we are going to do, this too will be covered next week tutorial. But we will cover one question from this sublayering today, and shell method determining asphalt modulus. This also we are going to do one question here. So discuss measurements and pre-assumptive values for subgrade and pavement materials. This part you have done in the lecture. Okay, so mainly we do some theory questions, and also we are going to do 2 numerical questions on these two. One is on sublayering of unbound granular materials, and the other one is on the shell method to find the modulus of asphalt. Okay, so let's start with the first question. Sketch and name the structural layers of a flexible pavement. So what are the layers of a flexible pavement? Yes, so you start. Yes. So you are building on your native soil, isn't it? We build on native soil that we call the subgrade. On top of the subgrade, we have the subbase, then we have the base, and then we have the varying course. Is that right? Okay. Now, they just ask you to draw and name, but now can you tell me what are the functions of these different layers? What they does? If you look at varying course, it consists of aggregates and the binder together. It's a asphalt layer, isn't it? And it's the one which is open to the vehicles. So periodically we have to do maintenance. We will get pothole patching, and that's the surface which need to be maintained. And also it prevents penetration of the water from the surface to the underlying layers. If water penetrates, it will damage the pavement layer. So it prevents that. And also it provides a smooth, well-bonded surface free from particles. It provides the comfortable drive on the pavement, and also skid resistance. So all the functional requirements are satisfied by this varying surface, because that's the one which we can see. The other layers are very important for structural part, taking the load and distributing the load, but this varying surface is the surface that we see on the road, isn't it? Now, how about the base course? If you consider the base course, that is the principal structural component which take the loads, traffic load, and we should select materials with sufficient quality, and we need to have the right thickness. We will discuss how to find the right thicknesses next week. And also it withstands the stresses produced in the base itself. And it resists vertical pressures that tends to produce consolidation and result in distortion of the surface course and resist volume changes caused by fluctuations in its moisture content. If you look at the sub-base functions like the base course. It's same as base course, but it is used to distribute the wheel load. The material requirement for the sub-base are not as strict as those for the base course, since the sub-base is subjected to lower load stresses. So if you look at the stress distribution, in flexible pavement, stress is distributed like this. Underneath the wheel, and you can see it is distributed grain to grain. So stress, when you consider the sub-base, the stress is less compared to the base. Okay, so because of this, the way that we are going to do design is different in the flexible pavement and also in the rigid pavement. In the rigid pavements, the load is distributed due to the flexural bending, but here it's transferring grain to grain. Any question? Okay, when you look at the question number 2, state and briefly discuss the main input variables for pavement design. So to do the pavement design, that means to select the right material and the right thicknesses. What are the input variables? Depending on what we do the design. What is the main thing?
What kind of intersection is that? Whether like cars are moving over it or if they're stopping?
First thing is the traffic load, isn't it? We need to know the traffic load that we are expecting. So when we consider the traffic load, we only look at the heavy vehicles for structural design part, because light vehicles can't structurally damage the road. But when you look at the geometric design, we need to know the whole volume, even the light vehicles and the heavy vehicles. But when we do the structural design, we are ignoring, we only take the heavy vehicles. What are the heavy vehicles? The trucks and yes. So I will show you a picture next week, how we, what category of vehicles are heavy vehicles and what categories cars and other light vehicles are the light vehicles. So, and when we consider that, it's not just the kilonewton load. We need to know how many axles that we have in heavy vehicles, in axle, how many tires that we have. Because if you see, as I showed you here, it's very critical how many number of tires are there, because the force or the load is concentrated just below the tires. So depending on how many number of axles you have, how many number of tires you have, and also the speed, that all matters when we consider the traffic load. All of these things are very important. What else? What are the other things that we need to know? What input variables? We need to know the traffic load. What else? Yes, environment is important. Temperature and moisture, because depending on the temperature and moisture, the material selection will be different. So yes, environment is important. What else?
Like the bearing capacity of the
subgrade, yes, the soil, the characteristics, where we are going to put the pavement, that is important as well. So that's three things. What else? There are 2 more things. Project reliability, that means how much percentage we can guarantee the project will last. Like we designed for 20 years for flexible pavement, for example, 40 years for rigid pavement. So, but we can't, we have a reliability there. We can't say it is 100% will be there. So we'll make it to 95% or 80%. So that percentage that we call the project reliability. So if you look at here, the project reliability is the probability that the pavement, when constructed to be chosen design, will outlast its design traffic before major rehabilitation is required. So it can be 95%, 90%, something like that. And also it is important to know the construction and maintenance considerations. It's not only the heavy vehicles going on the road, that the equipments that we use for construction and maintenance also can damage the pavement. So we need to think about those things as well. And as you have mentioned, the subgrade evaluation, the CBR of the subgrade. So these are the 5 things, 5 input variables that we need to consider for pavement design. So without knowing these 5 things, we won't be able to select the right material and also the right thicknesses for pavements. Are we good? Any question? Do you need time to write down? So tell me when you finish, okay? This all taken from your notes anyway. Okay. Third question. Name 3 differences between flexible and rigid pavement. There are many differences. So they're asking you to name just 3 things. So what are they?
Rigid has higher wearing force.
Yes.
And then
Yes. So okay. So there, this table is in your lecture notes. So if you look at this one, deformation in subgrade is transferred to the upper layers. So if in the flexible pavement, if something happened to the soil, subgrade is your soil, that is transferring to the upper layers. But when you look at the rigid pavement, deformation in the subgrade is not transferred to the subsequent layers because you have a concrete there. But for the flexible pavement, the layers are not concrete, they're asphalt. So the load is transferring grain to grain, even from the, if something volume instability or moisture, if something happens to the native soil or the subgrade, that effect will be comes to the upper layers as well. Second one, design is based on the load distributing characteristic of the component layers. But here, design based on the flexural strength. I already told you, in the flexible pavement, load is distributed grain to grain. But in the rigid pavements, it is like, it's like happening like bending, due to bending, like a beam. But here, the load will be concentrated just below the wheels. Flexible pavement has low flexural strength, so they can't bend. It's like, do you understand this one? This one has high flexural strength. So it's strong, rigid. So it's when you push in somewhere that will bend like this. But if you push the asphalt concrete, that will just make a dent kind of a thing. It's not flexural. Load is transferred by grain to grain. There is no phenomena called grain to grain in the rigid pavement. Have low completion cost, but repairing cost is high. So flexible pavements are cheap to construct, but maintenance costs are high because frequently we need to do milling and filling and those things. But in the rigid pavement, construction cost is high, but repairing, we don't have to do frequent repair maintenance like in the flexible pavement. Flexible pavements have low lifespan and rigid pavement have longer lifespan. So maybe 20 years here, maybe 40 years here if we can't go. That's why we are making highways, the motorways with concrete. We can't do maintenance frequently. And also it should last for a long time. Even though the manufacturing cost is, construction cost is high, it worth. 7, surfacing cannot be laid directly on the subgrade, but a sub base is needed. So you can't lay the base on top of the native soil in flexible pavement. You need to have a sub base as well. But here you can have a concrete on top of this native soil. No thermal stresses because in rigid pavement, concrete expand and contract with the temperature changes. But in so they can have cracks. We need to provide expansion joints. So the next one is expansion joints. Expansion joints are needed and thermal stresses are there in concrete. But if you look at the flexible pavement, they are flexible, so they don't crack because of the temperature changes. So there are no thermal stresses and we don't need expansion joints. 10th one, strength of the road is highly dependent on the strength of the subgrade, because if something happened to the subgrade, that will transfer to the upper layers. But here, the strength of the road is less dependent on the subgrade strength. Rolling is needed, but here rolling is not needed. But curing is needed in the concrete, so it takes about 14 days to cure the concrete properly. But here, within 24 hours, the rolling can be done and you can open the road to traffic. Force of friction is less. Here, the forces of friction is high. So you can feel when you drive. Concrete is more friction. The surface is more friction, with more friction. So the flexible pavement can damage by oils and chemicals because the bitumen react with the chemicals. But if you look at rigid pavement, it's not reacting with oils and greases. Are we all good? So you just need to write 3 things. There are many other things here. So when you understand the differences, you don't have to remember them. It will eventually comes if there is a question. Any question? No? 4th question. The flexible pavement shown in the figure below consists of dense grade asphalt. And so we have a dense grade asphalt layer at the top. So this is the asphalt layer. And 450 millimeters of normal standard unbound granular material. So we have unbound granular material layer here underneath the asphalt layer. They are asking us to characterize the modulus of the unbound granular layer using the Austroads method. So modulus, finding the modulus is very important. When you do the Circley experiment, we have to give that values, modulus of different materials. So here, modulus of the subgrade, if you know the CBR, have you done soil? Have you done soil before? So you know the bearing capacity of soil, isn't it? So CBR, if you can find the CBR, you can do a test and find the CBR. And if you know the CBR, you can find the modulus is just times by 10. So this is 30 megapascals. So you can consider the subgrade modulus. You can calculate the subgrade modulus just by multiplying by 10. Is that clear? CBR. California bearing capacity. Bearing ratio, sorry. And this one, this asphalt modulus is given to us in this question. Am I right? Asphalt modulus is given to us. Subgrade CBR is given to us. If you know the CBR, we can find the modulus of the subgrade, and they are asking us to find the modulus of the unbound granular material. How they have got this, we are going to do that one in the next question. How this 3000 came, we learn it in the next question. But now let's concentrate on this unbound granular material part. So here, when the Austroads method, it says, Austroads method, it says, we need to sublayer the unbound granular material. If this unbound granular material is not on top of a cemented layer, we need to sublayer it. So in our one, we don't have a cemented layer underneath the unbound granular material. Am I right? Cemented layer means bonded aggregates together, cemented. Aggregates are bonded together. So unbound means they are not bonded. They are just like aggregates. So if we have an unbound granular material layer, just aggregates staying together, just compacted. If it is just on top of the subgrade, we need to follow this Austroads method to find the modulus. In case if it is not on the subgrade, if we have another layer, cemented layer here, we are not following this sublayering procedure. Does that make sense? Okay, let's see what is the sublayering procedure. In the sublayering, what we do is, we divide this unbound granular material into 5 equal thicknesses. And we find the modulus of the first layer using an equation and also using a table. So I'll show you the equation. So when we find these two numbers, for example, in the equation it gives you 400 and the table is giving you 390. We ignore the higher value when we go with this, the lower value. Okay, so now let's see how we can do it. So we first divide into five layers, and the equation that we need to use is this. So the equation that we need to use is this one. Shall we do this together now? So you can find the first, this is the top layer. When you divide it into 5 layers, this is my first layer. You can find that one using this equation. What they say? Modulus of the underlying material. What is the underlying material? Unbound granular material. Underlying material for the unbound granular material is what? See, the subgrade, isn't it? The modulus is 30. How did we get 30? I told you, if you know the CBI, you just times by 10, you get the modulus. So this will be 30. So 30, then you need to times by 2 to the power of total granular thickness. So what is the total granular thickness? 450 divided by 150. So if you put this in your calculator, what do you get? (364 megapascals, okay, roughly 364 megapascals. Now we need to select, we need to refer to tables and we need to find the value from the tables as well. So table 6.4 and table 6.5 from the Austroads. So I'll show you these two tables. We need to first select the right table among the two. So now let's see the tables. So first table is suggested vertical modulus of top sublayers of normal standard material. The next one is suggested vertical modulus of top sublayer of high standard materials. If you look at your question, what the question says, normal standard or what is it? Normal standard. So we don't need this graph. So modulus of the overlying bonded material modulus is what? 3,000. Overlying material is 3,000, this one here. And thickness of the overlying bound material is what? Overlying bound material. 75, this one. So 75. So from the table, we get 340. From the calculations, we got 364. Now we got 340. We select the 340. So we know the other value and we go with the 340. Any question so far? No questions? So we go with the 340. What's that?
Oh, okay, it's in the equation. Okay.
It's from the equation, yes. Okay, now let's see how we can find for the other one. Now we need to find a ratio of this moduli. We can find the ratio using this equation here. So this R is equals to Modulus of the top granular sublayer. What is the modulus of the top granular sublayer? It is, it's the asphalt layer. It's not the top sublayers are these 5 sublayers. Granular, they're talking about granular, not about the bonded one. Do you understand the differences? This is granular, not bonded. This is asphalt concrete, where at bitumen and aggregate subway. It's not concrete, but instead of cement, we have used pine. This is a native soil. They are asking top granular sublayer. The one that we just found, which is 340.
So we don't use a 364.
No. Yes, we ignore this because we go with the lower value. We divide that by the underlying materials modulus. What is the underlying material? 30. And to the power of 1/5. What do you get? $1.63. What we do now is we divide 340 by 1.63. Then we get the next sublayers modulus. So what is the next sublayers modulus? $209. Next one, what we do? We take 209 and divide by 1.363. So then what is the next one? 128. Next one. They all are in megapascals, okay? 79 megapascals. Next one.
$49.
49 megapascals. So we found the modulus of the unbound granular layer. We follow the Austroads sublayering procedure. Why? We can follow it as this unbound granular material is just on top of the subgrade. Any question? No questions? If we summarize this, what we did, first we check whether the unbound granular material is on top of a cemented layer or the subgrade. If it is on a cemented layer, we are not going to do this sublayering thing. As it is on top of the subgrade, we do this sublayering process. So what we do in the sublayering, we divide it into equal 5 layers. And we first find the modulus of the first layer. To find the modulus of the first layer, we use the equation and we find it. And also we use the table to find it, compare the two numbers, and we select the lower value. Then we use the lower value and we divide the lower value by this ratio to find the next sublayer. Next sublayer's modulus will be divided by the ratio to find the next one. So likewise, we do the same thing till we finish the 5 layers. So you can see gradually it is decreasing. So at the top we have 3,000. Then we have 340, 209, 128, 79, 49, 30. Oh, good. Okay, any question?
Divided by 5.
Yes, that is the procedure. That is the method. Okay, so we'll move to the next question. So in the previous question, this 3000 is given to us as asphalt layers modulus is given to us. This 3000. Now we are going to look at how this 3000 came. How to find the modulus of the asphalt layer. That's our next question. So let's see how to find the modulus of asphalt layer. So these are there are different methods and we are going to use the shell nanograph method. So here they have given us the design speed of the road. T800 penetration of bitumen, the temperature which penetrates 1.1 millimeters of the binder. I'll show that equipment later on. This is the penetration index. This is the working temperature. This is the bitumen content in the mass percentage. This is the mass percentage of the binder, sorry, the bitumen, isn't it? And the maximum density of asphalt is given. Bulk density of asphalt is given. Bulk density of combined aggregates are given. So you are familiar with all these things. These are known. You have already done questions with these ones. This is also, you know what is the speed. And working temperature, that's the temperature, working temperature in different areas. So this in here, it is 27 degrees Celsius. For Sydney, it will be different. So likewise, we have different working temperatures. Now, I'll explain you this one, the penetration temperature and also the penetration index in a minute. So now let's see, before explaining that, let's see how we can find this. So are you familiar with this diagram? Okay, here, this is what they are asking us to find. Stiffness or the modulus of the asphalt. So we are going to find this. To find this, we need to know three things. First is the aggregate volume percentage, binder volume percentage, and also the modulus of the binder. So if we know volume percentage of aggregates, volume percentage of the binder, and the modulus of the binder, we can find the modulus of asphalt. So here you are talking about the binder. Here you are talking about binder plus the aggregate. Asphalt is binder plus the aggregate, isn't it? So any question? Do you understand this right-hand side table? Sorry, the chart. We can find this. How do we find this? I'll show you that as well. So here they have shown us. If you know the modulus of the binder, for example, if it is 20, you draw a horizontal line. And here you have volume percentage of the binder. If it is, for example, if they are taking it as 5, 10, I think. If it is 10, it is this line. And you draw a vertical line from there. And then if you know the volume percentage of the aggregate, here they have taken it as 82. You draw a horizontal line where it meets the this one here. This is the modulus of your asphalt. So that's how we are going to find the modulus of asphalt. Is that clear? We'll do the question, but you know how we do it?
I've never done this before.
No, you can't think and do. You have to do it beforehand. You need to have that experience. You should. That's why you have it in a tutorial. In one of the quizzes, I have seen this one sometimes ago. Okay, now let's see. Now let's see here. The stiffness of the binder or the modulus of the binder is not given to us. We need to find it. We can find it using this graph here. So this axis here gives us the modulus of the binder. To find that, we again need three things. Let's see the three things. So you need to know time of loading. You need to know the temperature difference between the penetration temperature and the working temperature. That is straightforward. That we know. Am I right? This one we know. Because 60 minus 27. Penetration temperature is 60. Go back to the question, 60 and the working temperature is 27. So that this is straightforward, which is 33 degrees in our case. And penetration index, if you know the penetration index, in our one we have -1. It's also given in our question, see? Am I right? So if you know the time of loading, I'll show you what is time of loading. You draw, this is your time of loading, for example, and if your temperature is this, you draw a line connecting these two points, and you draw a horizontal line with the time of penetration index, and then the intercept, for example, it is intercepting here. You draw a parallel curve where it cuts this one here, that will be your modulus of the binder. So that's how we do that part in the left-hand side chart. Are we good? Okay, so now you know how to use the chart, and now we are going to use our numbers to find out our one. Okay, so let's see what are these ones here.
So we're gonna get this in the next book.
I don't know. That's what I said. One of the quizzes, it was there. But I don't know whether you will be lucky enough to get this. I don't know. Okay, now let's see the rest of the things. Time of loading. Time of loading means 1 over the speed. So time of loading is equals to 1 over the velocity. So can you guys find me this one? Because we need to know the time of loading. Can you find this one, please? 0.025. Okay, so the temperature difference, we know that is 33 degrees. Penetration index is -1. Using these ones, can we find the modulus of the binder using the table now? Let's find the modulus of the binder. So these two we found, okay? So now we have 0.025. So you can see here, this is -10 to the -1, 10 to the -2. If you write this one, this will be 2.5 times 10 to the -2. So it should be between these 2 points, am I right? So it is somewhere here. And this number is 33 degrees. How did we find it? 60 minus 27, it is 33. So we found this point as well. Now we have drawn a straight line, and penetration index is -1. So we have, our point is here. Now we drew a curve, and it is where it is touching this axis here. This gives us the modulus of the binder, which is 35 megapascals. The thing, it's a log graph. You see it's getting expanded. It's not equal spacings. It's log. So when you get this kind of questions, different people will get different answers. It's okay as long as you show your working outs in the chart. So someone may say it is 36, someone may say it is 40. But if you, it can't be very different, but if you show your working outs, even though you have slight changes, that's fine. Any question up to here? Are you okay with finding this 2.5 times 10 to the -2? Yes. 33 is okay. Penetration index is given. So connecting these points and getting 35 megapascals. Is that okay with you guys? Okay, now we are going to use that 35 here. So that 35 should come to here. So where is that 35 in this graph? So this is 10. This is 10. This is 100. So 33 is somewhere, sorry, 35 is somewhere here. 35 is somewhere here. Am I right? Now we draw a horizontal line. We need to find the volume percentage of binder. So 5% binder content is not the volume percentage. It is the mass percentage. Am I right? That 5% is mass percentage. So you can use this equation now and find the VB. VB is VMA minus air voids. You're familiar with these terms now. What is VMA? What is air voids? You know those things. VG, volume percentage of the aggregates, also you can find using this equation. All of these ones, bulk density, maximum density, all are given. Bitumen content is given. Using these numbers, can you find these two? And using these two, can you find me these two, please? I'll give you a few minutes. So rho max is given to us, which is 2.450. Bulk is given to us 2.355 divided by 2.450. Make it to a percentage because we need it as a percentage. What do we get? 3.9. 3.9% is the AB. Okay. How about the VMA? 100 minus bulk is 2.355 over 2.603. Rho A is that. And 100 minus 4. I think you are right. 14%, right? Yeah. Yes. Now VB is what? And VG is what? Okay, this one is 10. Next one. 86. Okay. So we have these two. VB is 10%, VG is 86%. Anyone have any issues with calculating these ones? You already have done many times, so you should be fine with this. Only the VB and VG are new to you. The rest is okay. All good? Can I move on? Okay, now let's look at this graph. So we found we got the same numbers. Now where we are, we have 35 here. Am I right? We found this as 35. And this one is 10, isn't it? So 10, 10 curve. If you draw that, that is this one here. So I draw a horizontal line till it meets with this 10. So that is this one. 10, from where we got the 10? The 10 is this 10 that you found for VB. And then we need to draw a vertical line. And this one here is 86%. So we have 85 and 90. 86 is somewhere here. So you need to draw the 86 one where it cuts this line. That will be you're drawing a horizontal line from there. And again, this one is 10 to the power 3, that means 1000, and this is 10,000. So this number here is 6. So 6,500 megapascals. Are we good? So that is the modulus of the asphalt. 35 is the modulus of the binder. 6,500 is the modulus of the asphalt. In the previous question, the asphalt modulus was given to us as 3,000. Remember that? But that's how they have found it. So you can find the asphalt modulus using this method. And in the previous question, we learned how to find the modulus of unbound granular materials. Okay, so that's all we have for today. Are we good? Any question? No questions.
Are we getting a lot?
Most probably yes. Because your ones are marked.